Hello, everyone. Welcome to today's talk. Can you hear me?
Yes, now you are audible.
Yes.
Okay. Yeah, so it's my pleasure to introduce our speaker for today, Jan Hazla. Jan is the German research chair at the African Institute for Mathematical Sciences, Rwanda. He was recommended to us by Nancy Nadua from Pacific University. I think they have worked closely. So when I was talking to her, requesting her to give a talk, she was like, please get in touch with Jan. He's doing great work in the region, in East Africa and Africa at large. And I think many of us in the combinatorics community have benefited from some of the activities that he has been organizing. One in particular is the probability, information theory, and combinatorics summer schools, which usually organizes every year. So Jan, we are very happy and honored to have you speak to us today on the topic, weight distribution bounds for error correcting code relations. You'll be given between 40 to 50 minutes, and then after, we shall have some interaction through questions. You're most welcome, Jan.
Thank you so much, Olivia. Everyone can hear me?
Yes,
Yes.
we can hear you.
Okay. Yeah. So yeah, thanks a lot for inviting me, and also I appreciate this seminar series. I think it's a good idea to connect. And yes, maybe one logistical thing I mentioned before to Naina and to Olivia. Like I'm in Kigali right now. There is some chance there will be a power cut. So if I disappear at some point, don't run away. If you give me 5 minutes, I try to come back with mobile data. Hopefully it doesn't happen. Okay, other than that, yes. So this is the title of my talk, and it's based on a paper which has an even longer title. And it is a joint work with my PhD student, Donald Kugangiombi, who is also at AIMS Rwanda. And I will try to keep the talk as self-contained as possible. I also try to give some background before I discuss our paper. And yeah, feel free to interrupt at any time. Yeah, if you have a question, even to go back to the previous slide or something, don't be shy. Okay, so the area that, or one of the areas that I work on are error correcting codes. So let me start with giving like a little overview and also like set out the setting in which we are working. So an error correcting code is just like most generally, it is just a subset of some set of strings of length omega, where omega for us will be just some finitely sized set. And if the size of omega is equal q, then we will say that this is a q-ary error correcting code, and this omega, we can call it the alphabet. Okay, so most generally, the error correcting code is just a set of strings over a given alphabet of some given length. This length is often called the block length. Okay, so this n, which will be maybe the most important parameter for us, we call it the block length. And then another important quantity is called the dimension. And this is just the log q of the size of the code. So maybe more comprehensively, the dimension is the number k such that the size of the code, the size of the set is just q to the power k. And the way to think about it is that the elements of C, so these are called code words, they are used to encode some messages, maybe over the same alphabet. And then if size of the C is q to the power k, like assuming this k is integer, then you can think of it that any message over omega k, so any message over alphabet omega of length k, you can find some bijection, you can choose some bijection, and then use it to uniquely encode such a message as one of the code words. And like the broad pipeline, which is used, when studying these error correcting codes, is now when you have a message and then you encode it as a code word, then you apply some sort of a noise to it. And I do not define yet exactly what this noise will be, but it's some procedure or some rule against which we apply noise. And after that happens, we get a new string also in omega n, and this is like a noisy code word. So we start with a code word, and now after applying noise, maybe in some of the positions we will introduce errors, and now we get a new string. And the game now is to maybe find some new procedure, which is called another procedure, which is called the decoder, such that then it can take this noisy string y as an input and output the best guess it can have for the original code word. Yeah, so the idea is that we are sending some information, then this information becomes noisy, and now we want to recover it back to the original state. So this decoder, it's like in statistics. It takes y and then it gives as an output its estimate x hat of what the original code word was. And once you have this x hat, at least in principle, like because this encoder will be just a bijection, this is equivalent to also estimating the original message m by some estimate m hat. And from the point of view that I will be discussing today, in fact, I want to forget about this m and only focus on the x and y. Yeah, because at least if you do not focus on the efficiency considerations, this encoder is really just a bijection. So like in terms of the information content, x give you exactly the same information as m. So from now on, we'll actually forget about the m and the m hat. They are part of the story that motivate this setting. But really, we'll always be thinking of, we choose some code word, we apply a noise to it, we get y, and then we put it through the decoder, and then we try to estimate x hat. And once we define what exactly is the noise, what we want is to analyze or design C and the decoding procedure such that somehow, like in the end, we want to be able to decode reliably. So we want that this x hat is equal to x for like all or maybe most relevant combinations of x and y that we can have given how we define the allowed noise. And okay, now if you want this x hat to decode to x, like a trivial solution is to take a code which has just one element, right? If we have just one element to send, then like in any decoding, we can just go back to it and we will always be fine. So of course, we want to somehow trade off against something. And the most natural thing to trade off against is, of course, the size of the code, right? So, of course, when we are sending any sort of data for, efficient use of the bandwidth, we would like to be able to not have the k to be like very small compared to n. Because that would mean that to send one symbol of information, we are using many symbols of the code word. So for efficient data use, in principle, we want to find codes which have as large as possible their rate. And this is defined as just the fraction of k over n. Yeah, so k over n is just like how many symbols of a message you are sending per symbol of the code word. But of course, at the same time, we also want this protection from errors. So now the fundamental trade-off, which is kind of the foundation of this theory of error correcting code, is just this: rate versus error correction capability. Yeah, so somehow it is natural to think that like the larger rate you have, maybe the smaller the level of noise that against which you can protect yourself. And yeah, now one can study this more precisely, and this is what we will discuss next. One more mathematical point. So yeah, so from the point of view of theoretical study, it is often convenient to think in the regime where we take n to be large. So we will maybe make some asymptotic statements as n goes to infinity. And now I'm going to discuss two noise models, which are worst case, and these are the two most fundamental noise models I think studied, which are the worst case errors and the random errors, which are also known as a symmetric channel. And also for this explanation, it doesn't really matter too much what the alphabet is, but for most of the rest of the talk, I am going to also, for simplicity, to restrict myself. So to the maybe most fundamental case where this omega is just binary, so it is just 0 and 1. Okay, so now let's discuss these two modes of errors, and we start with the worst case, what is called the worst case noise. And for that, the fundamental quantity is called the Hamming distance. So, and the minimum distance of the code. So given two x and y in omega n, their Hamming distance is just the number of the coordinates in which they are different. And now the minimum distance of the code is just the minimum over all distinct pairs of code words of this delta of x and y. Okay, so it's just the smallest possible distance you have in the code between any pair of distinct code words. And it turns out that this notion, in a sense, it completely characterizes the performance of a code under this worst case model. And the reason for this is this claim. If the distance of the code is more than some 2e plus 1, then this code can correct any combination of at most e errors. Yeah, so this is the meaning of the worst case noise. We are asking for a code that can correct any combination of errors as long as there are at most e of them. Okay, and this claim it has proof like by one picture, and it goes like this. So if you go back to if you remember the first slide, like to the code, I first have to tell you what the decoding procedure is. And if you think about it, there is like a very natural decoding procedure, which is just if you get some y, just decode to the x, which is closest in the Hamming distance to which is a code word and is closest among the code words in the Hamming distance, closest in the Hamming distance among the code words from the y that you received. Okay, so this is maybe better illustrated in a picture. You start with some x, and then it gets distorted to some new vector y. And then as long as this y is at the distance at most e to the original code word x, if the distance of the code is more than 2e plus 1, for any other code word x tilde, the Hamming ball, so the ball in this metric of the Hamming distance of radius e around x tilde and the Hamming ball around x are going to be disjoint. And because they are disjoint, when I use this rule, when I come back from y to the closest code word in the Hamming distance, I am going to go back to the original x, so my decoding is going to succeed. Okay, and in fact, it's not hard to see that this is also like this notion of minimum distance. It gives you like the equivalent condition. So basically, the code of the distance delta n can just be set to correct this delta over 2 fraction of worst case errors. Yeah. So we have like 2e plus 1 here and e here. So there is like the one missing. But you know, in the regime where we think of large n, this is negligible. So I think like the upshot of this is for a correct error correcting code of distance delta n, such a code can correct around delta over 2 fraction of worst case errors. Okay, so now like one of the foundational questions of the coding theory is for a given delta, what is the largest possible, or for a given rate r, what is the largest possible distance for an error correcting code? Let's say for a binary error correcting code of rate r, right? This is like the quantitative version of this trade-off that mentioned in the beginning. And to talk about this question, I need to give one more definition. So this is called the binary entropy function. Okay, it's just a function on 0, 1 with this formula. And if you know information theory, then yeah, maybe you have seen it. It's basically the Shannon entropy of the Bernoulli. So h of x is the Shannon entropy of the Bernoulli distribution with probability x. Anyway, this is the graph of this function. It turns out that this function is very helpful to state many results in coding theory. And let me just, so, this is still background. So let me just give you quickly, so what do we know about this question in the binary case? So there is the theorem, which is called Gilbert-Varshamov bound, which tells you that given a delta between 0 and 1/2, you can construct binary codes of distance delta and the rate, which is up to small order terms 1 minus h of delta, right? So you see for delta from 0 to 1/2, this function is increasing. So 1 minus h of delta is decreasing. So this is really some relation where the larger distance you want, the smaller rate you are going to get. And so this is a construction. And then there is also an upper bound. Yeah, so this is also an odd result, which is often shortened to this MRRW. So for any delta, we can also prove an upper bound. So any binary code of distance delta must have rate less than something. And the something is pretty complicated. I did not write it down, but I can illustrate it. So the Gilbert-Varshamov is the blue line, and the upper bound, the MRRW, is the orange line. Okay, so we have two bounds for binary codes that, for a given relative distance, tells you what is possible. So they tell you, that it's possible to construct a code with the rate which is on the blue line, but we don't know. Maybe it's possible to construct a better one, but for sure it's not possible to go above the orange line. Okay, and then the area in between is where we don't know. And just what I want to quickly point out about these results, one is that this is like a very long-standing open problem, and you can see that the last progress that was made on this problem is in fact 1977. Yeah, so 50 years ago, and these curves have not moved since that time. So and by now people are writing papers about how. So in particular, I think there are papers written about why it is so difficult to improve this orange curve. Yeah, that many natural proof techniques cannot be extended to work better than this curve already is giving you. And maybe I can say also that I think the majority of opinion is that the truth is the blue curve. And yeah, so the question is really to decrease this orange curve all the way back to the blue. It seems this is one of these problems, which is now you can even think of it. It's like a historical open problem, which is still, we are stuck on it. So that's it about the worst case errors. Now I want to give background for the other model that I will discuss. These are the random errors. And yeah, since the errors are random, so here in this setting, I need to have some random variables and some probability. So the way to state it is as follows. Let's take some code, and let's take some parameter p, also between 0 and 1/2. And this will be, the probability of error on a single coordinate, like the error rate. And now we take x to be a random variable, which is just a uniform element of the code C. And we define y. So this will be the noisy code word as a random variable, such that for each coordinate I independently, you take xi and you keep it the same. So yi probability that yi is equal b given xi is equal b with probability 1 minus p. And because everything is binary with probability p, then you flip it around. So this is maybe better illustrated in the picture. Yeah. So for every coordinate, once you choose the code word, for every coordinate independently, you flip it to the wrong value with probability p, or you keep it on the correct value with probability 1 minus p. So this model is called the binary symmetric channel. It's denoted by BSC. And in fact, this decoding procedure that I mentioned, also on this channel, it's very intuitive, and in fact, it can be proved to be optimal in this model. So let's still consider the same decoding procedure, where this x hat is just given y, you find the closest code word to y in the Hamming distance. And now once you have all that, you have some random variable x, you have some random variable y, random variable x hat. And basically our job is to find the codes for which x and x hat are going to be equal with, like with as high probability as possible. Since this noise here is applied independently, like you cannot hope for probability equals 0, right? Like this is easy to see because with some small probability, maybe if you send all zeros, like it's just going, all the bits are going to flip. Yeah, in that case, it seems it will be hopeless to recover the correct message. So instead, we define the error probability in this random model to be just the probability that this random variable x hat is not equal to x overall. And then when we consider it asymptotically, so if we consider a family of codes with n growing, let's say that it works, that it succeeds on this BSC channel if this error probability goes to 0 as n goes to infinity. Okay, so this is our definition of being good in this error channel, because here we cannot say anymore you will always correct correctly. You want to correct with high probability, which means with probability going to 1 as n goes to infinity. And just as with this Gilbert-Valshamov and then MRRW, there are also fundamental bounds in for this random model. And this is even older and like even more exploited. So this is called the Shannon's coding theorem. And somehow he managed to prove like the optimal bounds on this in the same time as he actually stated this problem, more or less. And basically, again, this entropy shows up. So given P, there exists family of codes which will have the rate greater or equal 1 minus h of P. And at the same time, for any family of codes, n succeeds on the symmetric channel. And on the other hand, for any family of codes that succeeds on the BSCP, you cannot have the rate which is much larger than 1 minus h of P. Okay, so just to put these two pieces of background together and to illustrate, like maybe one question or like one suspicion you could have would be like, okay, but why should we study these random errors if we can study the worst case errors, right? Like if we have a code which is good for worst case errors, for the fraction P of worst case errors, it's also going to be good for the fraction P of random errors. So why not just restrict ourselves to the minimum distance? And the answer to that is that like if you allow random errors instead of the worst case errors, then you can get a better rate. So it's a real choice, right? If you want to be really sure that that you will only succeed, that you will succeed like in the worst case model, the rate you can achieve is lower than the rate on the in the random model. So this is the illustration of this, right? In both models, given a fraction of correctable errors, these are the best known binary constructions that we have. And you can see that there is a gap between them. And in fact, for the random error, sorry, I think this legend should be, it should be the other way around. So the blue line are the random errors and the orange line are the worst case errors. And you can even see that, in fact, for the worst case errors, you cannot do anything at non-zero rate above 1/4, yeah? Because for the worst case errors, we had this 1/2. If I have minimum distance delta, I can only correct delta over 2 errors. And because of that, it actually, this graph terminates at 1/4. So for these rates, you can protect yourself against like, let's say 45% of random errors, but you cannot protect yourself against 45% of, at all, against 45% of worst case errors at non-zero rates. Okay, so all of this is actually, this is not exactly what our paper is about, but now I can move to that. So now, once you have these two models, you can ask a question: what is can we have, or what is the best possible general relation between this worst case decoding and random error decoding? And more formally, the question is this: what is the largest fraction of random errors which is correctable by every binary code of distance delta n? So more formally, given delta, what is supremum of P such that for every code family with distance, minimum distance delta n, we have that this random error probability for P for this family goes to 0. Okay, so let's give some name to this supremum. Let's call it P star of delta. And the first claim, which is not hard to see, is that this P star of delta is at least delta over 2. And the reason for that is, I already alluded to it. So if you have a code of distance delta n, you know that it corrects delta of 2 fractions of worst case errors. So now if you take any p which is strictly smaller than delta over 2, you know, just by law of large numbers, if you now take errors in this random model, with high probability, with probability going to 1, the number of errors that are going to be made in the random model, the fraction of the errors that are going to be made in the random model will be strictly less than delta over 2. And when you get some combination of errors which and their number is strictly less than delta over 2, by this worst case decoding property, you are going to decode correctly using this Algmin decoder. So it is pretty clear that we get this P star of delta greater or equal than delta over 2. And kind of the question is really, can we do better than that? So can we prove that a code of the minimum distance delta, in fact, can correct maybe strictly larger than delta over 2 fraction of random errors? And let me cut out the suspense. So the answer will be yes. But to present it, I need to go through one more notion. And this is called least decoding. It is also a well-studied notion independently of our application. This is like a well-known subject in the theory of error correcting codes. And sometimes it is considered like a intermediate notion between this worst case decoding and random decoding. So a code, we will say that the code is, so there are two parameters, P and L. And we will say that the code is PL least decodable if for every string of length n, the number of code words which are at the distance at most Pn to y is at most L. Okay, so this is the illustration for L equal 3. For example, if L is equal 3, for the code to be P3 least decodable, it means that if I start at X, and then I distort it by at most Pn errors, now maybe the decoding to the closest code word is not going to give me back X. Maybe it will give me some X2 or X3. But if I go over to the distance Pn from Y, there will be at most 3 elements in there. And of course, the correct one must be among them. Okay, so this least decoding tells you that like maybe the worst case decoding is not going to be correct, but you can always output a list and a small list, and the correct element is going to be among the ones on that list. Okay, and then it turns out that there is another function which is somehow convenient for this least decoding. It's called the Johnson radius, and this is the formula. And the main result that we prove in our paper is that this P star of delta is in fact greater or equal than this Johnson radius. It's not just greater or equal than delta over 2, but it's greater or equal than this Johnson radius. And maybe before I discuss anything more, let me show you a picture just to convince you. Like from the formula, maybe it's not immediately clear, but you can see that, so the blue line is delta over 2. And what we can get is in fact strictly better than delta over 2. It's this orange line j of delta. And you can especially see like close to 1/2, like as in the worst case decoding, we terminate at 1/4, and actually this orange line, it goes all the way to 1/2. And the green line, okay, this is just, I'm not going to discuss it, but this is an upper bound. So you can also prove that this P star of delta cannot be more than delta. And now the truth is lying somewhere between the true P star of delta is lying somewhere between the green and the orange line. Okay, so let me quickly say that now the rest what I'm going to present, it's going to be for binary codes. However, the result itself, it generalizes, and the proof, they generalize in a natural way to q-ary codes. So this is going to work for any finite alphabet. And also let me say that like we are not the very first to prove a result of this form. So there is a paper from the last year where they proved this statement, but restricted only to linear codes. So a code is linear if if your omega is a finite field, and then omega n is a vector space, and then the code is linear if it's a linear subspace of this space. And our result like strengthens this to all codes. And also actually like our proof is very different to the argument that they are using in their paper. And the proof structure, it can be like cleanly divided into two parts. So the first one is to show, and this point in the middle is the least decoding. So first, we show that if the minimum distance is bigger than delta n, then the code is j of delta 2n least decodable. And you should think that this 2n, it's small. Like it grows with n, but it's still like compared to the size of the code, which is going to be exponential in n, this is a very small number. And this part is not new. This is actually, this Johnson radius. It comes from this bound. It is called the Johnson bound, and it was proved in the 60s. And then the part where we actually contribute is the second one, where we show that now, if you have a code family, which is P2n least decodable, or it doesn't have to be 2n, it can also be any polynomial or even more than polynomial, but just not too large. Then you get the binary symmetric channel decoding for every p prime strictly less than p. And if you remember the definition of p star, like now proving the theorem is just connecting these two implications and taking p equal j of delta. Yeah, because for the code of distance delta, we get j of delta least decoding, and then from the j of delta least decoding, we get the symmetric channel for every p star p prime less than j of delta. Okay. And for the rest of the talk, I'll just talk briefly how to prove. And I think, let me discuss both parts. So the first one, this is not by us, but I think it's like a very nice proof, and also it's quite combinatorial. So let's let me explain how we prove this Johnson bound. Okay, so now our objective is as follows. So here I just put, just that we remember, this is the definition of j of delta. This is what it means to be PL is decodable. And now our objective is to show that if I have a code of distance delta, then it is going to be j of delta 2n least decodable. And in fact, we are going to use a lemma, which is now not about strings, bit strings, but it's about vectors in Rn. It tells you something like this. If you have m vectors in Rn, which are non-zero, and for every distinct pair, their correlation is non-positive, then you cannot have too many of such vectors. In fact, their number must be at most 2n. Okay, and I'm not going to prove this lemma. The proof is not difficult, but let me skip it. Maybe instead let me illustrate it. So this is an illustration. Yeah, like if you take n equal 2, and I ask you to design some vectors, non-zero vectors, such that each pair of them has non-positive correlation, which means that the angle between them is either a right angle or more than a right angle. And if you try a little bit, you might realize that the best you can do is just to take some, take a standard basis and then take the negations of the standard basis. And like that, you are going to get 4 vectors which are, they're all mutually orthogonal. So in particular, they satisfy this condition. And it turns out that you cannot do better than that. Yeah, and the proof is not hard. It's just by induction on n. And once I give you a hint, it's an induction on n, then I claim this is like an exercise. So then it generalizes for an arbitrary n that the best you can do is 2n, because you just take the standard basis and the negations of the vector of the vectors in the standard basis. Okay, so assuming that lemma, how does the rest of the proof proceeds? So we want to prove that the code is P2n least decodable. So let's take some y and let's verify this condition for the y. So let's take this set, the set of all the code words which are at a distance at most j of delta n. And let's call the elements of the set C1 to Cm. So now all that remains to do is to show that the size of the set, that M is at most 2n. Okay, now for every Ci, let's define now, let's embed it. Let's make a vector Vi, which is in Rn, and let's define it as follows. So Ci is a bit string. It has zeros and ones. And now for the Vi, now in every coordinate, if Ci is equal 1, then we put -1. If Ci is equal 0, then we put 1. Okay? So it's just like encoding of zeros and ones by +1s and -1s in the space Rn. We do similarly for Y. So for Y, we also embed it in the same way, and we call the embedding R. And now it is not hard to see that the scalar product in Rn between this Vi and Vj, it is related to the Hamming distance by a simple formula. Yeah, because in the Hamming distance for every coordinate, if the coordinates of xi and of x and y are equal, then the Hamming distance is 0, and then the coordinates for Vi's are the same, so the product is going to be 1. On the other hand, if the Hamming distance is 1, then the coordinates is going to be different, and in the scalar product we are going to get -1. Okay, so if you put it all together, you see that the scalar product of Vi and Vj is going to be n minus 2 times the Hamming distance of Ci and Cj. Okay? But we know that the code has distance delta. So in particular, we know that this is at least delta of n. So now this Vi, Vj, we can upper bound it as 1 minus 2 delta times n for any distinct pair of Ci and Cj. On the other hand, what can we say about this Vi and R? Well, the first step is the same. The correlation, the scalar product of Vi and R is n minus 2 Hamming distance of Ci and y. But now we defined these C's to be those which are at a distance at most j of delta times n. So we know that this is now at most j of delta of n. So this is at least 1 minus 2j of delta of n. And now if you go back to the definition of j of delta, like you multiply by 2, so this this half disappears, 1 minus, you are just going to get square root of 1 minus 2 delta times n. Okay, now let's take some alpha greater than 0. And instead of Vi and Vj, let's consider vectors Vi minus alpha r and Vj minus alpha r. So what will be the scalar product between these two vectors? Well, we use linearity. So Va Vj, alpha Var, alpha Vjr plus alpha squared. And then the scalar product of r with itself, r just has -1s and +1s. So scalar product of r with itself is just n. And we substitute what we know already. So this is at most 1 minus 2 delta n. This is at least square root of 1 minus 2 delta, and these are two equivalent terms. So now I get minus 2 alpha square root 1 minus 2 delta, and here there is alpha squared. We can take n outside. And now if you just, I don't know, either look at it or solve the optimization, you see that now we can choose alpha to be square root of 1 minus 2 delta. And then it's going to be minus 2, 1 minus 2 delta, here plus 1 minus 2 delta, and here plus 1 minus 2 delta. Now we are going to get a 0 if we substitute alpha like this. So if we choose alpha like so, we get that every pair of these two vectors has non-positive correlation, and therefore by the lemma, there must be at most 2n of them. And this is exactly what we set out to prove. So this is the first part of the proof, which is done. Now, the second part is to show that if the code is P2n least decodable, then we are going to have a good performance on the symmetric channel. And for that, I need just a couple more definitions. So first, for a code and a string y and an integer w, which is between 0 and n, let's make a notation AW of y. Let it be the number of code words such that they are at a Hamming distance w from y. Okay? And the sequence of numbers like A0, so now for every y, you get a sequence of numbers, A0, A1 up to AN. And the sequence of numbers, often this is denoted as a weight distribution of C. And the second thing I want to introduce is, okay, so this is called nu of ntw. Okay, so it's the size of some set. What is the set? Is the set of all y's such that the Hamming distance of y from the all zero string is equal t, and also the Hamming distance of y from the string which is w1s and n minus w0s is also t. Okay, so in a more describable way, this nu of ntw, it is the size of the intersection of two Hamming spheres, right? So Hamming sphere is just a sphere in this Hamming metric. So it's the set of y's which are at a given distance from some point. And now here, this y, indeed, it's an intersection of two Hamming spheres of radius t. Yeah, it's at a distance t of some point, and it's at a distance t of some other point. And additionally, these 2 points are chosen to be themselves at the Hamming distance w, because I take 0 here and then 1w, 0, and minus w here. Okay, so it's some parameter. And now the crucial lemma, which is actually like not so difficult to prove, but it's kind of the basis of our whole method, is that now if I have a code which is p2n least decodable, then for every w, I can bound this quantity aw of y in terms of this nu of npn n of w. And the proof of this lemma is quite simple, so I think I still have time to quickly show it. So the way it goes is just double counting. So let's define the set S. Yeah, so I'm given y, and now I define the set S to be a set of pairs xz, such that x is a code word, z does not have to be a code word, and then the distance from x to z is equal pn, and the distance from z to y is also equal to pn. And now I'm just going to count the size of S in 2 ways. So starting from z and starting from x. So first, let's start from z. So for every z, by the least decoding property, the number, like for every z, how many x can be associated to z in this set? Well, the x's which are associated in this set to z are the ones which are at a distance pn, and they are code words. But if the code is p2n least decodable, then the number of x's which have this property must be at most 2n, just by the least decoding property. So therefore, the size of the set S is at most the number of possible z's times 2n. And what is the number of possible z's? Well, the z's are at a distance pn from y, so we can choose like exactly n, choose pn of them. Yeah? On the other hand, let's count the other way around. So given x, how many z's can I associate to this x? So let's assume that I take some code word x, and also that its distance from y is w. In that case, the number of z's that will be associated with this is just this, the number of z's which are at a distance pn from x and at a distance pn from y, and the distance x and y is w. So this is just this number nu I defined in the previous slide, yeah, of n, pn, and w. And now this is not for every x, it's just for the x at the distance of wy, but in particular it's a lower bound. So now the size of S is at least the number of such x's, so this is aw of y, times this nu of n, pn, w. And now the lemma follows just by rearranging. Yeah, like I got an upper bound, I got an lower bound, I put them together, and that's it. Okay, and from now on, maybe I'm going to speed up quite a bit. Yeah, so kind of this is the heart of the proof, and then we have to still use some existing probabilistic tools to conclude that once I have this bound on awi, I'm going to get that this error probability is going to 0. And this is done by something which is called a Poltyrev bound. So it turns out that there is like a known bound on this error probability for the code C at the parameter P. And this error probability is expressed in terms of this weight distribution AW of X. Yeah, so the same one that we bounded in lemma 1. and then some other numbers which are almost like this new of n, but a little bit different. So let me just tell you that the difference between this mu and nu is just that for this nu, this is an intersection of spheres, and for the mu, it's an intersection of balls. Okay? So basically, I get this bound on the error probability, and I am almost in shape to substitute here the bound from lemma 1. Like there is one more mismatch that has to be overcome, and this is that here I have balls and here I have spheres. So this bound is a little weaker than I need. However, then it turns out that at least up to lower order terms, this is not a problem, because in these high dimensional spaces, like maybe you have heard at some point, like, like when you take a high dimensional ball, most of its mass is at the boundary. Yeah, so the same holds for these high dimensional Hamming balls. So the volume of the sphere, the size of the sphere is not that much smaller than the size of the ball. And it turns out that this also translates to the intersections. So the size of the intersection of two balls is not much larger than the size of the intersection of two spheres. So in fact, these two values are comparable. So then with some technicalities that I'm going to skip, basically the rest of the proof is just like comparing these two numbers, concluding that the comparison is not too bad, and then substituting them and maybe using some monotonicity properties. Okay, so to conclude, yeah, like the main result that we have is that this value p star of delta, which is the best fraction of random errors that you can correct given minimum distance delta, we managed to show that it is greater or equal than this Johnson bound. As I said, all this method generalizes with some complications, but it generalizes to the case where you have like larger alphabets. For an upper bound, the best at least very generally, the best we know is delta. And so then the next natural question is like, okay, can we go better than this Johnson bound? And in fact, in the paper, we show something partial in that direction, but we only show it for linear codes, and it doesn't work in the binary case. It only works for larger alphabets, and the smallest one for which we can show an improvement is q equal 4. And the rest remains open. Okay, I think that's a good place to stop. Thank you.
Wow, thank you. Thank you so much, Jan, for this really insightful talk.